Nurseries want you paying $90 for pear trees that took them 50 cents worth of scion wood to create. But Chinese orchardists figured out 2,500 years ago that you can steal the genetics of any pear variety and force it onto wild rootstock that grows free in abandoned lots. They just turned worthless callery pears into premium Bartlett factories for $15, using grafting tape and a sharp knife. This is the nursery industry's worst nightmare, a backyard orchardist who refuses to buy their marked-up clones. Watch them perform plant surgery that turns garbage trees into gold. Fruit grown from seed produces entirely random genetics. Plant a seed from a sweet pear, and the resulting tree will likely yield hard, inedible fruit. Grafting is the biological workaround. By taking a living branch from a proven tree and physically fusing it to an established root system, you bypass genetic lottery and infinitely clone a specific, desirable fruit profile. This map illustrates the Silk Road project, detailing the specific overland routes where this cloning technique first migrated. Imperial Chinese horticulturists documented the method around 500 BC to ensure consistent crops for the emperor. As merchants traveled these trade arteries, the agricultural technology moved with them, reaching Persia by 300 BC and Rome by 100 AD, allowing European growers to standardize their own local fruit production. Mastering this ancient mechanic removes reliance on commercial supply chains. The ability to physically graft proven genetics onto wild roots allows any grower to bypass modern nursery markups and democratize access to premium agriculture. This photograph shows a mature callery pear, or Pyrus calleriana, thriving in a wild, unmanaged landscape. While its small, hard fruits are biologically useless for human consumption, its aggressive root system provides immense vigor, cold hardiness, and high disease resistance, making it the ideal biological engine for a newly grafted tree. Extracting this biological engine requires strict selection criteria. The ideal wild specimen is 1 to 3 years old, with a trunk diameter ranging from a pencil's thickness to the thickness of a thumb. The bark must be smooth and tight, completely free of the dark, oozing bacteriocankers that indicate underlying disease. You must dig up the tree in late winter while it is fully dormant. Extracting the root ball during dormancy minimizes physiological transplant shock. By excavating a wide circle a foot deep, you preserve the maximum density of fine feeder roots, the microscopic structures responsible for absorbing water and soil nutrients. Immediately after extracting and replanting the tray, you prune away 30 to 40% of its top canopy. This balances the internal water pressure. The severed root system temporarily lacks the pumping capacity to satisfy the water demands of a full canopy. Reducing the top growth prevents the compromised root ball from being exhausted. When placing the extracted tree in its permanent location, backfill the hole exclusively with the native soil. Adding nutrient-rich soil amendments creates an artificial textural boundary. The roots will circle within the amended soil, rather than penetrating outward into the harder native dirt, eventually strangling the tree. By treating the planting as an installation of plumbing rather than foliage, you decouple the tree's physical architecture. You secure a wild, aggressive, disease-resistant survival engine beneath the soil, preparing the site to eventually execute a total replacement of the worthless canopy above. The genetic payload you attach to the rootstock is called the scion. This is a 12 to 18-inch length of 1-year-old dormant wood harvested directly from the canopy of a desired parent tree. It contains the exact, unaltered genetic code required to reproduce identical fruit. This image highlights the speckled green skin of mature Bartlett pears. Known for their high sugar content, soft flesh, and excellent fresh eating qualities, Bartlett scion wood is heavily targeted by growers looking to establish an immediate, high-yield dessert crop on wild roots. In contrast, this photograph shows a single, russeted brown bosc pear. The bosc possesses a denser cellular structure that holds its shape during baking and allows for extended cold storage. Selecting scion wood from both trees allows a grower to graft vastly different agricultural tools onto the exact same root system. To preserve these genetics for spring grafting, the scion wood must undergo cold stratification. You wrap the cut bundles in damp paper towels, seal them in plastic, and store them at 35 to 40 degrees Fahrenheit. This specific temperature range locks the buds in a state of deep winter dormancy. This temperature manipulation imposes an artificial biological time delay. By keeping the scion dormant while the replanted rootstock wakes up and establishes new roots, you ensure the newly grafted canopy will not attempt to transpire water before the traumatized root system is actually capable of pumping it. Surgery begins in early spring, triggered by a specific biological condition. The rootstock bark must slip. When the bark peels easily, it proves the cambium layer, the thin margin of stem cells responsible for growth, is actively dividing and ready to accept new tissue. You prepare the dormant scion with a single 1.5-inch slanting wedge cut on one side. This exposes a long, flat oval of the bright green cambium tissue lying directly beneath the bark. On the opposite side of the scion, you make a secondary, shorter cut. This creates a blunt shoulder of wood designed to physically rest against the flat top of the severed rootstock, preventing the scion from sliding too deep under the bark. You then prepare the root system by cleanly sawing off the main trunk. Using a sharp grafting knife, you make a vertical 2-inch slit directly down through the slipping bark, gently peeling it back to expose the wet wood underneath. The physical insertion is a matter of strict alignment. The prepared scion slides beneath the bark, so the green cambium layer of the wedge makes flush contact against the green cambium layer of the rootstock trunk along its entire length. To secure the alignment, you spiral grafting tape tightly up the trunk with a 50% overlap. This applies immense mechanical pressure, forcing the two cambium layers to remain perfectly flush against one another. Finally, you seal the entire exposed wound and the scion itself with semi-permeable parafilm. This membrane blocks outside air to prevent tissue from drying out and dying, while remaining pliable enough for new buds to eventually push right through it. The complex geometry of these interlocking cuts provides absolutely zero structural strength. The shaping exists purely to maximize the microscopic cellular surface area where these two distinct plant species will attempt to bridge their vascular systems. In response to the surgical trauma, the aligned cambium cells on both sides of the cut immediately begin dividing. They rapidly multiply to fill the microscopic voids between the two pieces of wood with soft, undifferentiated cells known as callus tissue. For the first 3 weeks, this cream-colored callus acts as a biological mortar. It physically binds the two woods together but cannot transport fluids. The top of the tree is still entirely cut off from the roots. Survival relies on vascular differentiation. The chaotic block of callus cells begins to organize, forming structured vertical tubes called xylem. This connects the plumbing, allowing water and minerals to finally pump upward from wild roots into the waiting canopy. Simultaneously, a parallel layer of tubes called phloem forms alongside the xylem. This creates the return path, transporting the photosynthetic sugars generated by the new leaves downward to feed the root system. The circulatory loop is now closed. By month 3, the union achieves full lignification. The soft vascular tissues harden into solid wood, making the connection mechanically permanent. The two distinct species operate as a single organism. Maintaining this union requires strict physical intervention. The rootstock will continually attempt to push out its own wild shoots, known as suckers, from below the graft line. You must ruthlessly cut these off the moment they appear. If left intact, the aggressive callery roots will redirect all their water and energy to their native genome. They will actively starve the grafted scion above, causing the premium canopy to wither and the unified circulatory system to reject the graft completely. Once the basic technique is mastered, the geometry scales up. A grower can graft 3 or 4 entirely different pear varieties onto distinct scaffold branches of a single wild rootstock, creating a composite fruit library on one trunk. Managing this multi-genomic tree requires specific structural geometry. You must train the scaffold branches to sit at 45 to 60-degree angles. Branches growing entirely vertically produce heavy wood but little fruit. Branches growing horizontally fruit heavily but snap under the weight. This angle forces a balance of vigorous growth and structural integrity. You must also artificially balance the competing genomes through differential pruning. A vigorous variety like Bartlett is aggressively pruned in the summer, which drains its energy and slows its expansion. A weaker, slower-growing variety like Homis receives only minimal pruning in the winter, allowing it to retain maximum energy and catch up to the rest of the canopy. This image displays pear leaves with blackened, necrotic tissue, a hallmark of fire blight. This bacterial infection sweeps through commercial orchards, killing highly susceptible premium varieties rapidly as the bacteria travels down the branches and into the roots. A composite tree utilizes an asymmetric defense against this threat. If a grafted premium branch contracts fire blight, you simply amputate the infected wood. The wild callery rootstock below possesses a massive immune advantage. It prevents the bacteria from penetrating the root system, halting the systemic collapse of the organism and allowing you to regraft the next year. Through this process, a backyard orchardist ceases to be a passive observer. They operate as an architectural referee, artificially balancing the distinct metabolic demands and vulnerabilities of unequal genomes, all forced to share a single biological engine. Most pear varieties are not self-fertile. They require cross-pollination from a genetically distinct tree to produce fruit. A multi-grafted tree solves this structural bottleneck inherently. By placing Bartlett, Bosc, and Anjou varieties on the same trunk, they bloom simultaneously, cross-pollinating each other and closing the reproductive loop within a single footprint. A mature composite tree yields an exponential mathematical advantage. Every winter, a single successful tree produces over 50 lengths of dormant one-year-old wood. Each of those 50 branches is a viable scion. This abundance fuels an infinite propagation loop. Rare, highly specialized, and heirloom genetics that commercial operations abandon for lack of profitability can be rapidly multiplied and shared across informal neighborhood networks without spending a dime. The nursery cartels want you buying $90 trees every time you want a new variety. But Chinese orchardists proved 2,500 years ago that fruit genetics belong to whoever can graft them. Unearth the History is here to bring you the techniques they can't monopolize. Start your grafting rebellion today. Fuse the cambium. Subscribe to keep the resistance growing.